Hi everybody. My name is Ben, and I'm from spaceport.io. Today I'm going to be talking about perfmarks, which is our open source HTML5 benchmark test that we created to test rendering performance of various HTML5 rendering techniques among a variety of mobile and desktop browsers. So to begin with, why did Spaceport create perfmarks? Spaceport is a company that's designed to let developers use Adobe's tools to create cross-platform mobile apps. We support publishing to both native and HTML-based web applications. So when we were creating our HTML5 renderer, we had to decide which technique to use. It would be CSS, 2D transforms, 3D transforms, WebGL, Canvas. And rendering performance was a major consideration. Games tend to push the limits of number of objects and frame rates, so we wanted to find what was the best technique specifically for mobile browsers, which is the emphasis of what our platform is meant to address. So like any good engineer, we decided that we would benchmark it. And that's why we created perfmarks. Our methodology is to test translation, scaling, and rotation of images, sprites, being drawn in a variety of ways. We figure that games, one important aspect of games is moving images around on a screen. So that's a decent place to start for a benchmark for games. So what we are doing in these tests is moving around many images on the screen, and we see how many objects can be moved simultaneously per frame while maintaining 30 frames per second, and add objects until the browser is no longer capable of maintaining 30 frames a second, and that's the score that the browser gets. We figured this would be very easy to measure, right? No. What we found over the course of creating perfmarks is that getting accurate benchmarking data is very difficult. There's many complications that came up during the process that we had to confront, including the ones I will talk about today will be the JIT engine, latency with loading, memory problems specifically on mobile browsers, and screen updates, which I'll get to later. Overall, my conclusion about benchmarking is that getting data takes a long time, and that the results require a lot of scrutiny. You have to look over every number that you've got and make sure that it's valid and that there's nothing complicating it or making that number skewed in one fashion or another. So with our benchmarking suite, we began with code that looked something like this. You start running a test and draw 100 frames. On each frame, draw all of the objects. Then count the number of draws that have been made. If we've done all 100 frames, the test is done, and we see how much time it took. Otherwise, set timeout to give the browser a chance to refresh the screen and draw the next frame. So, what we figured was that the results would look something like this. The more things you draw per frame, the longer it takes to draw each frame. The results that you get from that code, however, actually look like that. It somehow takes less time to draw 30 objects per frame than it does to draw 15 objects per frame. This had us scratching our heads for a little while until we realized, oh yeah, the JIT engine. So the just-in-time engine kicks in after you've run code a reasonable number of times and decides, oh, I need to JIT this code. So it skewed our benchmarks to begin with. It meant that if we ran them in different orders, we got different results. So these were invalid results, and we had to fix this by sort of warming up the JIT engine. Let it run for a while until it has JIT the code, and then take the data. So one way we were able to solve this was to run the tests all twice and take the data from the second run. That fixed the first issue with benchmarking. Next issue. Since we're moving around a lot of images on screen, one of the methods we use is CSS 2D transforms or CSS 3D transforms to move around a lot of image elements. So if you have JavaScript code that looks like this, after the variable copy is assigned, would you expect the image to be loaded? Raise your hands if you would think the image would be loaded at that point in time. it's not in all browsers. It is in some. This basically did this. So we had some benchmarking numbers on Android 3.0 devices in the Android browser that were giving us really, really high numbers, excellent scores. Really? So apparently drawing, scaling, translating, and rotating broken images is very cheap. That was wrong. So what do we have to do about it? So this affected Android browser, mobile Firefox, Opera, and desktop Safari, but not mobile Safari. So it gave us some high benchmark scores. The solution was pretty much tons and tons of redundant on-load checks. This is also an issue for one of our other tests where we are using div elements with CSS background images specified. That's even worse because there is not an event listener for letting you know when the background image is loaded. What this means is that we simply are unable to get accurate benchmarking results using that particular technique on Android 3.x using the Android browser. So I'm not going to be reporting any data about that. The next problem we had was how many is a good number of objects to test run against. So the first simple sample I was showing you there, the number of objects was simply chosen from a sequence that was hard-coded like this. We got a graph, we found where that would intersect approximately 30 frames a second, and reported that as the approximate number. This is not very good. There's a couple problems with this. The biggest is that it just didn't go high enough for some browsers that had exceptionally high performance, and wasn't high enough resolution where others were. So the next pass was to simply add 25 rerun until the browser can't make 30 FPS, and then set it to a smaller step size and hone in on things. So the problems you encounter with this is first that real-world data is fuzzy. You can't binary search very effectively if you could potentially get a faster run by running more objects. Second problem is that real-world data is large. Counting to 7,025 at a time just takes a really long time. And we were running this test on a lot of browsers on a whole lot of phones. So this is a terrible technique. A technique that worked pretty well was to do a loop of estimate, test, re-estimate. So we would run the test for a certain number of objects, create an estimate of how much time it takes to render one object per frame. Use that to revise our estimate of exactly how many objects will that intersection point be at, test that many objects, and refine the estimator of time to draw object per frame. That pretty rapidly hones in on a reasonable number and then wavers around due to deviation in the test. And we simply terminate the test once it is looping. It's testing tests that have already been run. We also ensure that there are a couple data points above and below to make sure we can interpolate nicely. The next problem that we encountered with benchmarking was memory. On many of our mobile devices, just running our benchmarks would hard crash the browser. So we were getting no results. So what we were doing, we thought was reasonable but wasn't, was to generate test data ahead of the run. We didn't want to be benchmarking math operations or string concatenation. So what we did is we pre-calculated all transformations for all frames for all objects. And then when running the tests, simply assign these pre-calculated transformations. Simply test how long the drawing took, not calculating sines and cosines. And then when we were finished running, we destroyed all the data and reran. So this kills the garbage collector. This type of memory profile that you see here, with all those little spikes in between each test run, that is a terrible thing to do to a mobile browser. Just don't do that to mobile browsers, they hate it. What we did to fix this was we did some caching. So what we did is we saved the transformations that had been generated for objects for frames, and when later tests requested more that had been generated, added more and appended that to our cached value. So that we could not wastefully recalculate transformations. And if you look at the memory profile for this type of test, you see it increases rapidly as it's approaching the correct number of objects that can run at 30 FPS. And then when it's honing in on almost the correct number, the peak slows down in slope and approaches a certain number, at which it has calculated the number, and then when the test is fully done, clear out all the memory before running the next different test. This was a lot better on the browser memory, and the garbage collector didn't require it to do quite so much work. It was easy for it to garbage collect everything in a whole, so this stopped all those crashes. I would recommend that kind of technique for any kind of mobile application. So at this point in time, our code looks something like this. Somewhere along the line, we stopped just doing 100 frames and started making it time-based. So we ran the test for a certain number of seconds and then estimated the FPS based on how many draws had happened in the elapsed amount of time. So look at the code for a second. It basically calculates the start time. The draw function draws all the objects, increments the draw count, and revises the estimate of FPS by simply the number of draws that have happened in the number of seconds which have elapsed thus far. Still using set timeout to finish the thread and let the browser do a rendering call, and then do the next draw, basically spamming it as hard as we possibly can. So the problem with this is, in certain browsers, the screen doesn't always update. So rendering calls are being made at a particular rate, but the screen is being updated less frequently. So 2 or 3 draw calls may be being made, either by drawing to a canvas or by moving around a div, but the actual screen updates slower. So we were getting really, really high numbers, and we were suspicious, so we looked into it. And if you're watching it as a human, you can tell the screen is not updating at a rate of 30 frames a second. It's slower, it sort of looks choppy. You can tell that frames are skipping. So this stumped us for a while. We were not sure what to do about this because this previous technique, it doesn't know when the browser is updating the screen. This didn't affect all browsers, but fortunately there is something you can do about this when you're benchmarking. So a new HTML5 feature called Request Animation Frame comes to the rescue. This is a callback that you can register for that is only called when the browser is actually rendering to the screen. So the problem is that it is not implemented in all browsers right now, but this, when available, lets you accurately count the number of times the screen has been updated. So one could use that type of code to create benchmarking code that actually only counts the draws that have been made from the perspective of a user, by simply listening for that event. Our benchmarking code, in order to be consistent and run the same exact loop on browsers that do and do not support request animation frame, runs the set timeout. However, if request animation frame is available in the browser, we use that to count the number of draws, so that we can know that we're running exactly the same code, spamming it as fast as we possibly can, but have a more accurate frame counting. Okay, now I'll talk about the results. What did we find after we did all this and scrutinized our results and made sure that we were reporting numbers that are actually real? So our major comparison that we did with our last benchmark suite was to compare smartphones to laptops. Okay, why compare smartphones and laptops? There's a couple reasons. One is you don't develop on a smartphone. You develop in a web browser on your computer. So it's a nice thing to know if what's running quickly as you're developing second to second is actually going to perform at all when you run it on a smartphone, if that's the target that you're developing for. The next thing is when you're designing a website. When you're designing your website, you might have made a website that runs smashingly well in your desktop browser, but when people browse to that site on their mobile phone, is it going to run well at all? And the last reason is I think there's a major disconnect in the industry, which is, on the one hand, we have technology enthusiasts and hobbyists who are creating amazing, beautiful, sexy demos of WebGL and web workers and all sorts of cool stuff. And on the other side of the industry, we have the VCs and the businesses who are interested in creating mobile applications, who see these demos and think to themselves, oh, HTML5. I don't have to make 3 different native applications. I'll just make a cross-platform HTML5 web app. And you have to take these desktop demos and benchmarks with a grain of salt. The fact that it runs well on Chrome on your MacBook doesn't mean it's going to work particularly well on your iPhone. So in these tests, we compared top-of-the-line hardware on both ends of the spectrum. We took a modern up-to-date, brand new MacBook Pro running fully updated software compared to a brand new, fully updated modern iPhone 4S to compare Safari on mobile versus Safari on desktop. And we compared a brand new MacBook Pro, same hardware again, to the Samsung Galaxy S2. So we tested a variety of Android devices, and when it comes to HTML5 performance, the Samsung Galaxy S2 got the best of all the devices that we tested, among the Nexus and various others. Android 4.0 got the best performance of all the different Android operating systems that we tested, and Google Mobile Chrome Beta was the fastest Android browser that we were able to find. So one little caveat is that we did not exactly test Safari on the web browser. We actually used a WebKit nightly build because request animation frame was not available in stock Safari 5.0. So the WebKit build that we used has the Safari icon, and when you click on About, it says Safari 5.0. So we figure it was pretty similar, but in the sake of complete honesty and disclosure, it's actually a WebKit nightly build. Okay, so here's the results for Safari. So, as you can see, on the MacBook Pro, the fastest technique for rendering is Canvas. This is pretty impressive. 7,000 sprites able to translate each frame is not bad. That's pretty good. So interestingly, so the only difference between these top two techniques here is that on the top one it is pixel aligned, meaning that when we call the draw image function on the canvas, we math.floor the x and y coordinates to make sure it's perfectly pixel aligned. That seems to have a major benefit. We're thinking that most likely this indicates this has been special cased, that there is a sort of hot path for this. That gives you pretty tremendously awesome performance there. The iPhone 4S is also having the same performance characteristics, which is kind of nice. The fastest thing on desktop Safari is also the fastest technique on mobile iOS. It's getting 400-ish, 450-ish objects, translating, rotating, and scaling per frame, which is the best we've seen on a mobile browser. So this is quite an impressive number for a mobile browser. It doesn't seem to benefit from pixel alignment particularly. It's probably using the same code path for both of these. We speculate there might be potential gains that can be made if there's a special case made available for the pixel alignment in the future. Sadly, WebGL is not supported on the iPhone 4S or any mobile Safari. However, it has pretty awesome performance when you are on the desktop. Interestingly, not as good as Canvas. Our speculation is that it doesn't have to do some bounds checking, it doesn't have to do some error checking in the Canvas case because it knows the inputs and those have to be performed on the WebGL. CSS 3D transforms have the next best performance characteristics, still fairly good. On the 4S, you're able to get 100 to 140 frames, or objects moving around each frame while maintaining 30 frames a second, and about 1,000 on the desktop browser, so that's relatively good. It seems that on the mobile browser, you're doing slightly better by moving an IMG tag around than you are moving a div element. And then CSS 2D transforms appear to not be hardware accelerated. Okay, Chrome. Chrome is a very different story compared to Safari. Unlike Safari, where we saw the same performance characteristics in terms of ordering for the desktop and mobile browser, it's very different here. So Chrome is getting a phenomenal 4,000 objects being drawn per frame when using Canvas on the desktop. However, in Chrome mobile beta on the Android 4.0 using mobile Chrome beta, we're not even able to get one object moving around each frame and maintain 30 frames a second. So it seems that there's a ton of room for improvement here when Google moves the code that is doing all the hardware acceleration for their Canvas into their mobile browser implementation. As with iOS, sadly, mobile Chrome does not support WebGL, which makes us sad. But again, excellent performance on the desktop implementation. Once again, I was surprised to learn that WebGL was not as fast as Canvas. CSS 3D transforms are your best bet for HTML5-based games for mobile Chrome. You're able to get about 60 to 70 objects moving around each frame. And that is also relatively good on the desktop browser. And once again, CSS 2D transforms is not hardware accelerated, it would seem. One interesting thing to note here is that pixel alignment doesn't seem to make a difference for Chrome on the desktop as it did back here with Safari. So there's potentially even more wins to be made on the mobile Chrome browser here by special casing this as well. If you are interested in running the perf marks on your own computer or your own smartphone or a different browser, or if you want to look through our methods or copy code, it's open source, feel free to go to our GitHub page and clone the repo at github.com/perfmarks. And you can see the report summarizing this data at the Spaceport website at Community Perfmarks. And I'm in for questions. Any questions? Yes?
One of the slides you showed this problem with cloning images.
Yeah, let me find the cloning images problem. I think that's here.
How it affects performance as you actually add the download handler in an app. It's not something that you're using in an application. So it doesn't have the best by the overhead or the best function, which may be different from viruses.
The question is, does adding an onload listener affect the performance of the test? So the answer is no. We load all of the images beforehand and simply wait until they're all loaded and remove the listeners before starting the test. The reason we had to add them in the first place was to wait to make sure the image is being drawn to avoid doing this. But we wait until all of them are finished loading before we bother to begin testing and timing. Other questions? Yes?
Do you happen to test phone 7 at all?
Say again?
Do you happen to test phone 7?
Windows Phone 7?
Yeah.
No, I'm only presenting the data on Chrome and Safari. Like I said, it's really hard to get accurate benchmarking data, so we need a little bit more time to make sure that the data we report on everything is pretty accurate. Yes?
Were you ever able to actually measure the display frame rates and stuff, what the code setup is?
Yes, the question is, are you able to measure the display updating? That was what I was mentioning with the, the request animation frame. So this is a new feature of HTML5, which is supported in certain browsers. When you listen for this callback, you are basically the browser lets you know when it's going to draw the frame from the user's perspective. It's a pretty cool thing to use when it's available. Okay, thank you very much.